Swayam Prabha. Digital India. Educated India.
Okay, so in the previous class, so we basically looked at properties of single valued function, and especially their differential is an exact differential, right. So we basically defined what do we mean by exact differential. We looked at few properties, right. So basically what we did, if we have a function which is a function of two variables x and y, and for its differential to be an exact differential, the first property is that its cyclic integral has to be 0, and also its double derivative with respect to x and y, right. It is independent of how we take that derivative, whether we take derivative with respect to y first or x first or vice versa, right. And we also derived some very useful theorems. So one of them was reciprocity theorem, which goes as follows. So for such a function, so we can write del x by del y at constant z times del y by del z at constant x times del z by del x at constant y, that is minus 1, and this is known as reciprocity theorem. And we also derived what is known as reciprocal theorem, which is del x by del y at constant z is basically inverse of del y by del x at constant z, and this is true for all the derivatives, right. Okay. And using some of these quantities, using some of these properties, especially this property, we derived a set of 4 Maxwell's relationships, which looked as follows. So the first one was minus del p by del s at constant v equals del t by del v at constant s, right. So this was the first relation. So the second one was del v by del s at constant p equals del t by del p at constant s. This was the second relation. So this was derived from the first law of thermodynamics, essentially the internal energy being the function of natural variables s and v. The second one was enthalpy, where the enthalpy's natural variables are s and p. Similarly, for the Helmholtz potential, so we saw del s by del v at constant t equals del p by del t at constant v. This was the third Maxwell relation. And for Gibbs potential, so del v by del t at constant pressure equals minus of del s by del p at constant temperature, and this was the fourth relationship, right. So using these thermodynamic potentials, we basically derived set of these 4 Maxwell relations, right. And we also towards the very end, we also discussed what is known as Joule expansion, right. It is an adiabatic expansion of gas molecules into emptiness, essentially, right. Okay. So in today's class, what we will do is we will essentially use all these properties in one way or the other, first to derive first to basically learn the Joule expansion of a real gas, and later on we will apply some of the ideas that we have developed so far of thermodynamics to non-gaseous systems. Okay. So let us start with what we ended in the last class, which is the Joule expansion. Right. And quickly I will just go through it. So essentially the problem is as follows. So we have a container where there is a wall, and all the gas molecules are occupied in this half of the container, and this container overall is insulated, right. So it can't really exchange any heat with the surroundings, and what we do is we expand this gas suddenly such that, so basically we open this channel and all the gas molecules, they are now free to expand into this empty area, right. And the question that we are asking is as follows. So, again this is insulated. Okay. So, the question that we are asking is as follows. So, we defined something known as Joule coefficient, Joule, Joule coefficient, and this is mu j, and this is essentially the change in temperature as we increase the volume of the gas under adiabatic conditions, right. So, it can't exchange heat, so the entropy remains constant. Okay. And basically we are interested in what happens to the temperature of such a gas, right, when it undergoes such a process. Okay. And in the last class we quickly saw that for an ideal gas, right. So, what is an ideal gas? So, the molecules, they do not really attract each other, there are there is no potential energy contribution to the total energy. So, all the internal energy contribution comes from kinetic energy, right. It all depends upon how individual gas molecules are moving, what are their individual speeds, and what is their kinetic energy. So, it does not matter whether you contain those molecules in a bigger container or smaller container, their kinetic and total kinetic energy is not going to change, right. So, we saw that for an ideal gas, since u is only a function of temperature, right, so therefore, so del T by del V, right. So, temperature, which is a measure of basically the internal energy, so this is 0, right. So, therefore, the Joule coefficient for an ideal gas is 0, right. Now, the real thing is like what happens when your gas is not an ideal gas, right, what happens for a real gas, right. So, basically what about a real gas? Right. So, what is the mu j coefficient, the Joule coefficient for a real gas? Okay. So, now remember, like real gas is little bit more complicated because not only individual molecules have kinetic energy contribution to the internal energy, but there is also intermolecular attraction, right. So, therefore, it depends on an average how far these gas molecules are from each other, right. So, therefore, in general the internal energy of a real gas is not just a function of temperature, but it turns out it is also a function of volume, right. And what is volume? Volume basically dictates how far individual molecules are on average with respect to each other, right. So, we have this function which is a function of T and V, and now we will now start using the techniques that we developed in the last lecture, right. So, let us start with the reciprocity theorem, right. So, if I apply reciprocity theorem here, so you just have to compare this with z equals z of x y, right. And remember we wrote so del x by del y at constant z times del y by del z at constant x times del z by del x at constant y equals -1. So, I want you to like apply the same formula here, and so this is the reciprocity theorem. So, therefore, we can write del T by del V at constant u times del V by del u at constant T times del u by del T at constant V, and this is -1, right. And now we are going, so this is reciprocity theorem, and now we are going to apply what is known as reciprocal theorem, right. And that basically tells us this del x by del y, sorry del z, it does not matter actually, del z at constant y equals 1 divided by del z by del x at constant y, right. So, this is the reciprocal theorem. So, we will apply this theorem in this equation, and we can rewrite it as follows. So, that basically becomes del u by del t at constant v times del t by del v at constant u equals minus of del u by del v at constant t, right. So, essentially what I have done is I have just moved del v by del u on the other side and inverted the denominator and the numerator, right. So, del u by del t at constant v remains the same and del t by del v at constant u remains the same. So, I have just use the reciprocal theorem. Okay. And in fact I can rewrite it like this again, right. So, del T by del V at constant u. Okay. So, I am going to use reciprocal theorem again. So, this is negative of del u by del V at constant t. So, this is V, okay, times del T by del u, right. So, I am going to invert this, del T by del u at constant V. Okay. And the reason we did this is because now the left hand side of this equation del T by del V at constant u, right, is essentially mu j, right, because during the adiabatic expansion, even if it is an ideal gas, the total internal energy still is constant, since there is no heat exchange with the surroundings. So, so S and U both are constant, right. So, this is essentially mu j, and this can be written as negative of del u by del V at constant t times del T by del u at constant V, okay, and this is the mu j. Okay. So, now we are going to just basically use some of the definitions that we have learnt in this course. Okay. So, remember how we defined the heat capacity at constant volume, right. So, heat capacity at constant volume is basically CV, and by definition this is del Q by del T at constant volume, right. And also remember from first law, if your volume remains constant, so the change in heat is equal to the change in internal energy, right, because P times dV is 0, right. So, if V is constant, dV is 0, and this is basically exactly equal to del U by del T at constant V, right. And in fact, I can now write my del T by del U, right. So, so which implies del T by del U at constant V is 1 divided by CV, right. So, if I substitute it back here, so therefore, my mu j becomes minus 1 by CV times del U by del V at constant temperature, or I can write del U by del V at constant temperature as minus mu j times CV, and let us call this equation number 1. Okay. So, now let us write first law of thermodynamics, right. So, from first law, essentially the statement of first law is that du equals TdS minus PdV, right. And what we can do is we can take its derivative with respect to volume at constant temperature on both sides, right. So, taking partial derivative with respect to volume at constant T, right. So, this becomes del U by del V at constant T equals T times del S by del V at constant temperature minus P, right. Now, we are going to use the third Maxwell equation, right. So, remember from third Maxwell equation, del S by del V at constant temperature equals del P by del T at constant volume, right. So, this is the third Maxwell relation that we have used. So, this one del S by del V at constant T is del P by del T at constant V. Okay. And now, we can basically just substitute del S by del V at constant T with del P by del T at constant V. So, therefore, my this equation can be written as follows. So, del U by del V at constant T is equal to T times del P by del V at constant del P by del T, okay, del P by del T at constant V minus P, right. So, I have just substituted del V by del T del S by del V with del P by del T. Okay. Now, we also know from the equation number 1 that del u by del v at constant t is minus mu j c t, right, mu j c v. So, therefore, this is this is right. So, this is basically just negative of C v times mu j equals T times del P by del T at constant volume minus P, right. And from here finally, we can write the final expression of the Joule coefficient which we are interested in as minus 1 by C v times T times del P by del T at constant volume minus P, okay, and this is the final result, right. So, this is the final result for a system whose internal energy is both a function of temperature as well as volume, right, and such systems are typically like real gases that we encounter every day, right. Alright, so this is an important result, but let us check. Okay, so we already know that mu j should be 0 for an ideal gas. So, let us see if this expression gives us that, right. So, so clearly, so for an ideal gas, and let us for simplicity just use 1 mole of gas. We know P v equals R T, right. So, which implies P I can just write as R T divided by V, and if I compute del P by del T here. So, del P by del T at constant volume is basically just R divided by V, right. So, if I substitute that value here, okay, so I am just going to substitute. So, therefore, mu j equals minus 1 by C v times T times R by V. So, T times R by V minus P, right, and this is what, minus 1 by C v times V times R T minus P v, right, and we know P v equals R T for an ideal gas. So, this is 0 for an ideal gas, okay. So, this relation indeed gives us 0 for the Joule expansion in case of an ideal gas, okay. So, essentially what that means is, so this essentially implies we can never cool an ideal gas, cool or heat, right. We can't really change the temperature of an ideal gas by doing adiabatic expansion or compression, right. An ideal gas upon adiabatic expansion, okay. So, this is the first result, right. So, which we basically earlier we just qualitatively saw that this should be the case, but now we can see it by using this formula, okay. So, now let us apply this to a real gas, right. So, now for a real gas, so we are just going to use the real gas equation, right. So, which is for 1 mole, which is as follows. So, P divided by P plus A by V squared times V minus P equals R T, and I can rewrite my pressure as follows. So, pressure can be written as R T divided by V minus P minus A by V squared, right. And if I take the partial derivative, so essentially I am just going to compute the same term. So, del P by del T at constant volume, right. So, that simply becomes R by V minus P, and the second term is 0, okay. So, now let us put this value again into this relationship. So, therefore, for a real gas, mu j is minus 1 by C v times T times this quantity, right. So, R T divided by V minus B and minus P, right. And to simplify this, now we can again substitute the value of P from this equation. So, this is minus 1 by C v times R T divided by V minus B. So, minus R T divided by V minus P plus A by V squared, and you can see that these two terms cancel out, and the final result that we get is mu j equals minus A by C v times V squared, and this is the result for a real gas, right. So, you can see it is non-zero first of all. For real gas, then mu j is not 0, it is non-zero, and the other important thing is that it is always negative, right. So, the heat capacity can never be negative, because you always need heat to heat up a system, right. The volume can never be negative, and also the A, right, the correction term that we did in the ideal gas equation, which arises due to the intermolecular attraction, that is also always positive, right. So, therefore, mu j is less than 0 for a real gas, right. And what is, again let us go back to the definition of mu j. So, mu j was basically the change in temperature by changing the volume, and this being negative means increasing V decreases temperature, right. So, if I expand a real gas adiabatically, so its temperature will go down. Okay. So, that is okay. When from this formula we can see it is negative. So, now let us try to think it conceptually, right. So, why is that happening? Okay. So, for that I will again go to the intermolecular attraction potential that we typically have between molecules. Okay. So, what I am going to do is, so again I will just draw it little bit bigger. So, typically the interaction attractive potential between two gas molecules. So, this is R, this is V of R, this is usually 0, right. So, this is 0 and values below this are negative, right. So, so say when we have not expanded the gas, so the gas molecules are sitting here, right. So, their mean intermolecular distance is say R 0, which may be like corresponds to two molecules being separated by R 0, right. And remember, this system is still insulated. Okay. So, this system is insulated, it can't really exchange heat with surroundings. So, one constraint or one condition that will always remain true is that its internal energy cannot change upon expansion, right. So, before expansion, this is the typical potential energy. So, maybe I can do it with a blue one, right. So, before expansion the potential energy is somewhere here, right. So, this is the potential energy, let me call it initial, right. Say the total internal energy is somewhere here. So, this is the total energy, again this is initial, I will get rid of this drawing. Okay. And since total energy is this, potential energy contribution is negative. So, its kinetic energy, initial kinetic energy is somewhere here, right. So, this is kinetic energy initial. Okay. And now after expansion we are going to increase the volume, and increasing the volume essentially means the intermolecular separation is increasing on average, right. So, therefore, this point will basically climb somewhere here, okay, which basically means the molecules are now farther apart on average, right. So, let me just call it Ri. So, this is Ri, okay, this is also Ri, and this is Rf. So, this is after expansion and this is what Rf corresponds to. Okay. And now you can see very easily that after expansion the potential energy moves up, right, it moves up the potential hill. So, this is potential energy, let me call it final, right, after the expansion has happened. But remember, the condition is that the total energy cannot change, right. So, the total energy of the system before and after expansion remains equal, right, it does not change, that is the condition. So, now since we are moving this potential energy up, which has a negative sign, in order to preserve the total energy, the final kinetic energy has to be lower, so that the sum can be preserved, right. So, therefore, after expansion the kinetic energy, let me call it final, goes below, right. So, therefore, in order to preserve the total energy, so the kinetic energy after expansion is less than kinetic energy, initial kinetic energy. Okay. And what is kinetic energy? That is actually the measure of temperature, right. So, therefore, if we adiabatically expand a real gas, since its total internal energy does not change, its temperature goes down, right. So, this implies cooling, right. So, this is like an intuitive and intuitive way of understanding this problem, and again like the formulation that we developed initially, which is the kinetic theory, that comes in handy, right. So, it is always useful to visualize these systems as collections of these molecules which are attracting each other, which are colliding each other, and so on, right. So, it becomes really in some sense trivial to basically understand some of these results, right, which we obtain using the laws of thermodynamics. Okay. So, after this, so now what we will do is, so we will basically, okay. So far you must have realized, or you must have seen that most of the things that we have been discussing in thermodynamics, we always take the example of gases, right. So, we always use real gases or ideal gases as our examples, right. So, it might give you an impression that thermodynamics is only true for gases, but that is not true, right. So, thermodynamics can also be very faithfully applied to non-gaseous systems, right. And in the remaining time of this lecture, we will basically apply these ideas to two more systems which are actually not gaseous, right, and let us see how we can do that. Okay. So, basically thermodynamics applied to non-gaseous systems. Okay. So, again we will see the first law, right. So, remember according to first law, so from first law implies the change in internal energy is basically sum of heat supplied or released from the system plus work done by the system or work done on the system, right. And typically, so for gases, right. So, for gaseous systems, so this work we usually define as minus P times dV, right, because that is how we look at this, right. And when we so the gas typically has a pressure and it has a volume, and the work done is given by the pressure time the volume, right. So, this is how we define the work in case of gaseous systems, right. But this definition is only limited to gases, right. In fact, we can define something known as a generalized work, right, which does not have to be only for gaseous system, right. So, let us define what is known as generalized work, right. So, generalized work let us again call it dW, and this does not have to be pressure and volume, but it can be anything like which can look like x time dx, right. So, capital X times small dx, where of course, in this case x corresponds to pressure and v corresponds to small x, right, for gas. And you can look at this definition again, right. So, here pressure is an intensive quantity, right, and whatever happens, whatever comes in front of the differential is an extensive quantity, right. So, where x is an intensive variable, and whereas small x is an extensive variable, right. And for gases, capital X stands for pressure, which is an intensive variable, it is independent of the size of the system, and small x stands for volume, which is obviously an extensive variable since volume scales with the size of the system. Okay. So, keeping this picture in mind, now let us move on to the first example, right, first non-gaseous example. So, example 1. And this is basically a solid rod, okay, solid rod. So, let us see how we can understand the thermodynamics of a solid rod. Okay. So, say we have a rod which is hanging from top, and it is under certain stress F due to its own weight or something, and the length it corresponds to is L, right. So, this rod can be metallic rod, it can be rubber band, it can be anything, right, but it is not gas, all right. And say we apply slightly greater amount of tensile force. So, this is tensile force because it is stretching this rod, right. So, if I apply F plus dF to this system, if I add little bit of more load, then the length of this rod changes by dl, right. So, clearly, okay, so clearly in this case what is the work done, right. So, so in this case the work done, the generalized work that we defined here, like x time dx basically becomes the force, which is the tensile force, multiplied by the change in the length, right. So, this is the amount of work this force is doing to increase the length of the rod by an amount dl, and F is, like I said, is basically tensile force, and you can very easily see that it is an intensive variable, right. Whereas the dl or L, this is a okay. So, dl is change in length, okay. So, this is what the F and L are playing the roles of x and capital X and small x for such a generalized force, okay. And there is something very useful quantity which we define as an isothermal Young's modulus, okay. So, Young's modulus, okay. So, I will define that. So, usually when we are dealing with rigid rods, there is a material property which we define as isothermal Young's modulus, which is denoted by the symbol ET. ET stands for being isothermal, right, and this is basically the definition of any modulus is basically stress divided by strain, okay. But while the temperature of the system is kept constant, okay. So, how do we define it, right? So, remember, like I said, say at certain force F, the length of the rod is L. If I give a tiny increment to this force dF, the length increases by dF, right. So, therefore, I can define my stress. So, what is stress? By dimension, stress is basically force per unit area, right. So, the extra applied force dF divided by the cross sectional area, right. So, this is cross sectional area, which is A. So, this is divided by A, and what is strain? That is a dimensionless quantity which is change in a variable divided by its absolute, like its initial value, right. So, this is dl by L, okay. So, this is by definition, this is how we define an isothermal Young's modulus, okay. And you can see that this can be simply written as L divided by A times del F by del L at constant temperature, okay. And remember, this Young's modulus is really a material property, okay. So, if I use a rigid rod made up of steel or iron or copper or anything, they all have their own material property, right. It depends upon how these atoms or molecules they are interacting with each other and so on, okay. So, this is really a material property, and which is usually very useful in when we use these objects for various applications, okay. And we will define another quantity known as linear expansivity. Okay. So, linear expansivity which is defined as alpha f, and what is this? This is fractional change in length, right. So, fractional change in length. So, del L by L as a function of temperature while we keep the tensile stress constant, the tensile force constant, right. So, it is like saying I am holding a wire or rod or anything, and I am giving it a certain tensile stretch to it, and say I increase the temperature, how much will the length change, right, while keeping the force constant, okay. And if you remember, this is similar to, okay, so similar to So, similar to this expansivity that we defined in case of gases, right. So, we defined similar to isobaric expansivity, I think 2 classes before, which we denoted as a symbol beta p, and this is fractional change in volume of the gas as we increase its temperature while keeping the pressure constant. Okay. So, it is in the same spirit we have just applied this definition to a linear system, right, since we are dealing with rods and we are giving it tensile forces, tensile stresses. So, we define another quantity which is linear expansivity. Okay. And another important thing to remember is this linear expansivity is usually positive for metallic rods, right. So, if you have a copper wire or a gold wire or anything, so if you increase the temperature, right, its length will increase, right, it is essentially saying it's linear. So, if you increase T, the L will increase, keeping the force constant. Okay. So, this basically like I just said. So, rods expand upon heating, right. However, there are also some systems where this alpha f is not positive, it is negative, and this is usually true for polymeric materials like rubber bands, right. So, for polymeric rods like rubber bands. And I do not know whether you have played with rubber bands ever. So, if you heat a rubber, it actually contracts, right. So, contracts upon heating. Okay. So, essentially what we will do next is we will basically apply the similar law of thermodynamics to this system and understand and basically calculate various quantities like entropy, heat release and so on. Okay. So, let us start. Okay. So, now the quantity, the function that we are interested in, the quantity that we are interested in is the length of the rod, right. So, therefore, let us define the length function, which is now a function of temperature, right, as well as the force, right. So, the length of the rod can change either by applying certain force or heating it up or cooling it down and so on. So, therefore, the two natural variables in this problem are now temperature and force. Okay. So, again we will use the reciprocity theorem. So, use reciprocity theorem, and by using that, so we can write it as del T by del F at constant L times del F by del L at constant T times del L by del T at constant F, and this is equal to minus 1. Okay. And if I use reciprocal theorem again, so I can write del F by del T at constant L equals negative of del F by del L at constant T times del L by del T at constant F, right. So, what I have done is I have just moved this on the other side, right. So, del F by del T at constant L equals negative of del F by del L at constant T and del L by del T at constant F. Okay. But remember what is the definition of isothermal Young's modulus, right. So, that contains del F by del L at constant T, right. So, this quantity. So, I can just substitute. Okay. So, maybe I can write. So, remember E T, which is the Young's modulus at constant temperature, we saw this was L divided by A times del F by del L at constant T, right, and also the linear expansivity as 1 by L. So, alpha f as 1 by L del L by del T at constant F. Okay. So, if we now substitute these values here, so we can see that the left hand side del F by del T. So, therefore, del F by del T at constant L simply can be written as minus E T times A divided by L times alpha f times L, right, and this cancels out and we are left with minus alpha f A times E T, and let us call this equation number 1. Okay. So, that is the first, that is the important result. All right. So let us try to again visualize this result, right. So, remember I said for metallic rods, right. So, if alpha f is positive, that implies del f by del t at constant length is also negative, right. So, is negative, right. So, if alpha f is positive, then this is negative, and all this means is that, so now I want you to use your imagination. So, you are holding a rod by applying certain force, and you are making sure that the length does not increase, right, and you are applying certain force. But now if you start heating up, right, if you increase the temperature, so if you increase the temperature, since this quantity is negative, you need less and less force to maintain that length, right. That means the rod is slackening, right, it is losing its rigidity. So, this basically implies rod slackens, right. So, basically it loses its strength, right. And if you keep on increasing the temperature, of course, the rod will melt and you will require absolutely no force to hold it, right. But again, for the other case, for polymeric materials, I will explain what do I mean by polymeric materials. But remember, the example that I have in mind is a rubber band, like rubber band, right. So, alpha f is negative, and if alpha f is negative, then your del f by del t becomes positive. So, remember, E t can never be negative, right. So, Young's modulus can never be negative, you always need some force to basically stretch something, right. And this implies, now again if you imagine, so I am holding a rubber band to maintain its length, and I am increasing the temperature, right. So, since these rubber bands, they tend to contract, shrink upon heating, I have to apply greater and greater amount of force as I increase the temperature, right. So, which means the rod, so the rod becomes stiffens, okay, stiffens, right. So, so basically its rigidity increases, okay, it becomes more and more rigid, right, it becomes stronger in that sense, okay. So, that is like first result that we can already imagine happening, okay. So, now let us try to calculate quantities like change in heat and entropy and so on, okay. So, again applying first law, so from first law we can see du equals dq plus dw, right, and this is basically TdS plus FdL, right. And now I have a plus because, okay, so earlier we had a minus, right. So, when we deal with gases, we have minus PdV, because as we increase, as we apply pressure, as pressure increases, volume decreases, right. So, they are opposite. But on the other hand, here when I apply force, the length of the rod is increasing. So, therefore, I have to put a plus sign, okay. So, now let us define, let us do the Legendre transform and define the Helmholtz potential, right. So, therefore, Helmholtz potential in this case is F, which is essentially U minus Ts, right. It is the same Legendre transformation, and this becomes, if you take the differential of this is du minus d of Ts, right. And I will go to the next page. So, I will basically substitute du from here. So, this becomes Tds plus Fdl minus Tds minus Sdt, okay. So, Tds cancels out. So, we are left with minus Sdt plus Fdl, and this is df, okay. So, clearly we can see the S is negative of partial derivative of f with respect to t at constant length, and small f is partial derivative of Helmholtz potential with respect to length at constant temperature, right. And also since f is an exact, df is an exact differential, so del square f by its two natural variables are t and l, del t del l, del t del l, so this is t, equals del L del T, right. And now I will basically split this into two. So, this is del by del T of del F by del L, right. So, del F by del L is small f, right. So, this, so from here, right, so from here I can write del F by del L, similar to how we derived Maxwell equation. Essentially we are basically deriving the Maxwell equation for this system, okay. So, this becomes del F by del L, so del F by so del F by del T, okay. So, del F by del T at constant length equals, so del by del L of del F by del T, which is S. So, del by del L of S at constant temperature with a minus sign, okay. And this is the equivalent of Maxwell relation, right, in context of these rigid rods, okay. So, okay, so now that we have shown this, so remember we saw in equation 1 that partial derivative of force with respect to temperature at constant length is this thing, right. So, therefore, I can write, so I will just substitute that, okay. So, substituting, okay, so substituting LHS like left hand side from equation 1. So, we end up with del S by del L at constant temperature equals, so the negative sign cancels out, this is alpha f A times E T, okay. So, A times alpha f times E T, okay. So, this is f, and this is an important result, okay. So, this is one. Now, this just tells us that what is the dependence of entropy on length, and if I have to measure the change in entropy, so I can easily do that. So, change in entropy, say delta S is basically given by E times alpha f times E T times delta L, okay. So, this is the change in entropy upon stretching a rod by a length delta L, and since delta Q, the change in heat is T times delta, sorry, delta S is T times delta Q. So, we can also write delta Q as, okay. So, I am just substituting delta S as, sorry, so this should be Q. So, the change in heat delta Q is T times delta S, right. So, I can just write delta S as delta Q by T. So, this becomes delta Q equals T times A times alpha f times E T times delta L, okay. So, this is the change in heat, okay. So, these are the two important results, all right. So, now let us try to apply, let us try to see what are the signs of these quantities, right. So, case number 1 is when alpha f is positive, and this is true for metal rods, right. So, if your alpha f is positive, remember delta L is also positive, we are stretching the rod, E T is also positive, the cross sectional area is also positive, temperature is also positive. So, the only the parameter which is changing the sign is alpha f, right. So, if your alpha f is positive, okay, so maybe I can do it in a tabular manner. So, let us do metal rods, right, and the second example that we are considering is rubber band, right, rubber band. And like I said, for metal rods alpha f is positive, on the other hand alpha f is negative for a rubber band, for a polymer material. And if delta f is positive, your delta S will also be positive. If delta S is negative, this is negative. Similarly, delta Q positive and delta Q negative, okay. Okay, so what does that mean, right? So, that means if I stretch a metal rod, so delta Q will be positive, and what does that mean? So, that means the heat is released into the environment, right. Okay, sorry. So, the delta Q positive means system is system is gaining heat, right. So, it is absorbing heat from the surroundings. Okay. So delta, so this means heat absorbed, right. So, if the rod is absorbing heat, its heat is increasing. So, that is why it has a positive sign. So, heat absorbed from surroundings, and similarly the entropy increases. On the other hand, with the rubber band, due to the reason that alpha f is negative, heat is released to the surroundings. And also the entropy increases, entropy decreases. Okay. So in fact, this is something that you can very easily see, right. So, in fact, I have brought a rubber band with me. So, this is a typical rubber band that you see every day. I will try to give you a conceptual reason why this. So what do I mean by the polymer that I keep using, right. So, like I said, if I stretch a rubber band, right. So, our result tells us that the heat is released to the surroundings, right. So, that means the surrounding should heat up. So, this is a very easy demonstration that you can do at home. So, you put this rubber band between your lips and you stretch it very quickly, right, almost adiabatically. So, you can feel that there is subtle change, that you can feel that the rubber band is heating up. Okay. And similarly, you can do the other way as well. So, you start with the stretched rubber band, and if you very suddenly like it undergoes a contraction, right. So, it cools down, right. So, upon stretching it increases, and upon contraction it cools down. Okay. And this is basically the result that we got. Okay. But this will be the opposite for copper wire or something. It is not that easy to stretch a copper wire, but this demonstration works really well with a rubber band. Okay. And let us quickly go to the microscopic picture, right. So, remember what is an elastic or metal rod. So, metal rod is basically collection of many atoms, right, which are basically in a very ordered manner. They are like sitting in a rod, right. And when we stretch this rod, so what happens is, now these atoms, they have more space, right. So, we are increasing the interatomic distance between these atoms, right. So, when we increase the interatomic distance, there is more volume per atom available, right. And remember, like 2 classes or 3 classes before, we defined the entropy as the number of microstates available to every single molecule or atom in the system, right. And if I increase the volume which is available for every atom, that will only increase the number of microstates, right. So, it will have more position coordinates to explore. So, therefore, it has a higher entropy, okay, upon stretching. So, basically I am stretching in this direction. Now, let us go to polymers, right. So, rubber band is a polymer. So, let me define what is a polymer. So, polymer is a basically it is a huge molecule which is a chain like molecule, right. So many atoms, they are connected with each other through strong covalent bonds or something to form a chain like object, right. So, polymers are like this chain like objects, and this is what rubber band looks like microscopically, right. So, rather than having atoms as the individual building blocks, we have these thread like molecules which we define as polymers, right. And now, if I stretch it, right, what will happen, right. So, if I give you a tangled up thread and if you stretch it, it will elongate, right. So, after stretching, these polymers will tend to elongate, right. So, these polymers will tend to elongate, and since there is constraint that these molecules are always along a line, they are connected to each other. After stretching, there are fewer number of microstates, okay. And one way to understand that is using a crumpled sheet, right. So, if I give you a A4 sheet, if you crumple it up, right, if you make a ball out of it, there are many ways you can crush a sheet, right. So, if you just look at the individual creases and valleys and so on, there are thousands of ways you can create a similar looking crushed paper. On the other hand, if you have a stretched piece of paper, there is just one way you can like have a completely flat paper. Similarly, you can like tangle up a thread, in this case polymer, in many number of microstates, but if you stretch it, the number of microstates goes down. So, one way to think is, if I go to extreme limit where I just make a straight thread out of it, there is just one way. Of course, molecules can go interchange their positions between each other, but there are fewer number of ways in which I can put all these atoms in molecules in a linear chain, right. So, therefore, in this case the entropy decreases, right. So, that is why we acquire a negative sign here, and that is all the outcome of this linear expansivity being a negative quantity. Okay, so now in the next class we will now go into the second system, which is now the liquid films, right, and we will basically apply similar ideas to another non-gaseous system. So, thank you so much.